Electromagnetic induction. As of now, in electrostatic chapter, we studied about electric field because of the static charge. In magnetism, we studied current is responsible for the magnetic field. Now, using these things, we we are making ulta by changing the magnetic field, we are producing current. What we did as of now, we produced magnetic field due to current. Okay, we produce magnetic field because of current. Now we'll produce current using magnetic field. Understood this concept? The whole chapter is about this. And this current formation due to the change in magnetic field is known as induced current, not normal current, induced current. Any doubt, guys? Look at this. If you are calculating magnetic flux, it will be equal to B dot dA, and it is comparable with the Gauss law. In Gauss law, you know electric flux will be equal to electric field into area vector. Almost same thing. Any doubt? Everything is exactly same. Instead of electric field, you have magnetic field here. Understood, guys?
Yes, sir.
Scalar quantity because dot product. Unit is Weber. This Weber you can use even to calculate your magnetic field. If magnetic flux unit is Weber, to Hina, what will be the unit of magnetic field using Weber?
So Tesla meter square.
In the form of Weber.
What, sir?
In the form of Weber.
Yes, sir. I don't understand the question, sir.
My question is, in the form of Weber, what will be the unit of magnetic field?
I'm not sure, sir.
So you know magnetic flux is equal to B into a area vector. You want to
Yes.
calculate for the magnetic field, it will be magnetic flux per unit area. Unit of the magnetic flux is Weber and unit of area is meter square. Weber
Yes,
per
sir.
meter square. You said Tesla per meter square, right?
Yes, sir. Yes, sir.
Understood? Any doubt?
No, sir.
Again, like electric flux, we are using area vector, not area. Area vector is perpendicular to the plane. Okay, I will write here. Area vector is perpendicular to plane of given area. A given plane have particular area. For this, your area vector will be perpendicular to this. Area vector will be perpendicular to this, perpendicular 90 degree. And as you can see, both magnetic field and area vector have same direction. So your theta is 0. If theta is 0, cos Sarah, what is the cos 0 value?
1, sir.
1. So in this case, all the magnetic field line will pass through the area. All the magnetic field line will pass through the area. Logically, you can see if you have a ring like your hand, you can consider your hand as a ring, and magnetic field lines are passing perpendicular to this surface, definitely it will have maximum flux. Logically, it makes sense.
Yes, sir.
Yeah. Now, if area vector and magnetic field are perpendicular to each other, you take a ring and magnetic field is parallel to this, parallel, like your both hand are parallel to each other. Can your hand pass through each other? No. Correct. It's like how I explain the Fleming rules. Same thing I explain in the area vector of the electric flux. So if they have theta 90 degree, cos 90 0, then your magnetic flux will be zero. Sara, Chandana, I think two of you were there, if I'm not wrong. We did same thing in electric flux, and I told you how it will make difference, and all three answer were zero in the PYQ. Do you remember?
Sir.
Yes. Now you have Faraday's law. In board, people read about two laws. Faraday's first law says that electromagnetic induction or EMF is always due to the change in the magnetic flux. EMF is always due to the change in the magnetic flux. Second, magnitude of EMF is directly depend upon the rate of change of magnetic flux. EMF E is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux. Why rate? Because you have time in denominator. You have time in denominator. Okay. And you have change in the magnetic flux in the numerator. And minus sign is showing if you increase magnetic flux, your EMF will reduce. Direction is opposite. Understood? Direction is opposite. Because when you bring magnet toward the coil, then EMF will induce, but it will always oppose the change. Same thing is explained by Lenz's law. Whenever you try to do some change in the ring by changing magnetic flux, it will oppose the change. It will oppose the change. Same like we did same thing somewhere. Oppose the change. If you are increasing, it will decrease. If you are decreasing, it will increase. Oppose the change. Lee Chatelier principle. Do you remember, guys? In Lee Chatelier principle, we studied about it oppose the change. Whatever you do, it oppose the change. Same thing here in Lenz's law. It oppose the any kind of change in magnetic flux. So your EMF value will be equal to minus d phi by dt. Jordan, what is the significance of this minus sign?
I don't remember, sir.
No, based on what I just explained, what is the significance of this negative sign?
So the opposition to the flux, is that why the minus sign is there?
Yes, it's oppose that any kind of change happen in the ring. EMF always try to oppose the change. Okay. Second, EMF is like voltage. EMF is like voltage. So you can apply your Ohm's law. V is equal to IR. Instead of V, we have EMF is equal to IR. So R, I will be equal to E by R. Makes sense. And your E value was minus d phi by dt by R. मम्मी मिनमोसी अगली वह बात निरंजन गई थी काकड़ू बात निरंजन गई थी काकड़ू Any doubt, guys? Any doubt?
No, sir.
And you know I is equal to dq by dt. So dq will be I into dt. You already know I value and it will be multiplied with dt. इनका इनका ब्याह में कौन गया था बात नहीं होना इनने भी कार्ड भेजा था देख आए थे खुद आके भेजा था फोन में। एनी डाउट गाइस?
No, sir.
If a loop removed from the magnetic field, what will be the change in the magnetic flux? This. If you turn around the loop by 180 degree, why it is double? Example, you know your magnetic flux in first situation is BA. Magnetic flux of the second situation is minus BA because angle is 180 degree, right? Cos 180 is equal to, Chandana, what is the cos 180 value?
-1.
Minus 1. So it will be minus BA. If you want to calculate d phi in this case, it will be phi 1 minus phi 2. Phi 1 is BA minus BA. That was the reason why it is double. Understood, guys? When you are changing angle by 180 degree, because it is depend upon कि d change in d phi will be equal to phi 1 minus phi 2 or phi 2 minus phi 1. Okay, that's all. Next, Barinder, what is the meaning of this diagram in your opinion? What does it signify? You have one dot in the middle and then you have this circle. What does it mean?
Sir, clockwise.
क्या होगा?
Magnetic field in clockwise.
Magnetic field outward. If it is dot, outward. If it is cross, then inward. Correct? Cross means inward direction. And if it is dot, then outward direction. Any doubt? Now use Fleming right hand thumb rule. Fleming right hand thumb rule. If your magnetic field is outside, Pratigya, what will be the direction of current? Using right hand thumb rule. Thumb is toward you. What will be the direction of current? Use right hand.
Clockwise.
Anti-clockwise. Observe it again. Current will be anti-clockwise. And if your current is anti-clockwise, that's why it is north pole, anti-clockwise current. Understood? Anybody have doubt? Let me know. प्रतिज्ञा समझ में आया क्या?
सर आप क्वेश्चन क्या बोले थे बताएंगे?
मेरा क्वेश्चन ये था कि इफ योर मैग्नेटिक फील्ड इज आउटवर्ड डायरेक्शन, what will be the direction of the current? Clockwise or anti-clockwise? Using right hand thumb rule.
Clockwise.
Anti-clockwise. See, raise your right hand. Point thumb toward you. What will be the direction of the finger? Clockwise or anti-clockwise?
Sir, clockwise.
Clockwise, sir.
Anti-clockwise. See you from toward you. Thumb, your right hand thumb toward you.
So then
What is the
it'll be
direction of the
anti-clockwise, sir.
finger? Clockwise or anti-clockwise?
Anti-clock.
Anti-clockwise. It is anti-clockwise. Any doubt? So
No
let's
doubt,
take
sir.
one more example to explain the same stuff. Example, you have this ring. In this ring, magnetic field is present inward. This is magnetic field inward. If magnetic field is inward away from you, what will be the direction of the current? Clockwise or anti-clockwise? Tuhina,
So clockwise.
clockwise.
It will be south pole, no, sir?
Yes. And if it is clockwise, then it will be southward. Why? See, compare. Here also it is like this. Clockwise, south pole, anti-clockwise, north pole. Any doubt, guys? Anybody? How to calculate change whenever area is changing present in the magnetic field? You know pi is equal to B into A. If area is changing, your magnetic flux will also change. If magnetic flux is changing and divided by time, then it will give EMF. So in this case, you can calculate uh, delta phi value is equal to B delta A. So based on the change the area, you can calculate EMF. Example, if your area is increasing, what will happen? And magnetic field is inward direction in this case. If area is increasing and magnetic field in inward direction, so what will happen? Area is increasing. It depends upon the current. It will be anti-clockwise as you can see here. Okay. If area is decreasing, then current will oppose this. Why? You have to observe कि if you bring south pole, then overall structure will show south pole.
काट
Okay. So what is happening in this case? If you bring north, where should I write? I will write in the end. If you bring north pole to anything toward this coil, Sarah, what will be the pole shown by this ring? North pole or south pole? Sarah, are you there?
Yes, sir.
What will be the direction? What will be the pole shown by this coil if north pole is coming toward it?
The south also.
North pole. Why? Because according to the Lenz's law, Sarah,
Yes, sir.
whenever you bring any kind of pole, your coil will try to resist it, oppose it. So if north pole is coming, then you want to have north pole to oppose this. Any doubt?
No, sir.
If you see कि north pole is going away, what should be the pole shown by the ring, Jordan?
It should show south.
It should show south. Why? Because when north is going away, it want to
It
attract.
will attract, so it will show south.
Exactly. Chandana, if south pole is coming toward the ring, what will be the pole shown by the ring?
The south pole.
South pole. And Barinder, if south pole is going away, from the ring, what will be the pole shown by the ring? Barinder, North Pole. Got it? Any doubt, guys? Any
No,
doubt? So this is the simplest version of the Lenz's law. Ki whenever you want to, you are bringing some kind of magnet, some pole, your coil will resist the change. If north is coming, it will develop north. If north is going, then it will develop south because now it want to attract. Okay, when you are bringing north pole closer, it want to resist, means repel. When you are taking away north pole, then it want to attract. Okay, here it will show repulsion. Here it will show attraction. Any doubt, guys? Yes or no?
No, sir, no doubt.
no, sir.
Huh. So if loop is shrinking, like loop size is decreasing, you know EMF formula is this, and phi value is BA. It means it will be minus B delta A by T. In this case, area is equal to pi r square. If you do differentiation of r square, pi is common and different. Let me ask this question. Hmm. Pratigya, what will be the differentiation of dr square with respect to dt?
2R.
2r and dr by dt. Why? Because remember, you cannot differentiate r with respect to time. Not possible. That's why you do differentiation of r square with respect to r, and that's why we have dr here. If you do differentiation of dr square with respect to r, then answer will be only 2r. But here we have this thing extra. Why? Because we can't differentiate r with respect to time. Make sense, guys?
Yes, sir.
Hmm. These are the same pole like I showed it to you. Done. EMF is equal to BLV. So Hina, how we got this value? Because we knew that our EMF value was equal to minus d phi by dt.
Sir,
We knew that our d phi value, sorry, EMF value was d phi by dt. Then how we got E is equal to BLV? Motional EMF.
okay.
Yeah. How?
I'm not sure, sir.
So can you say this minus phi value will be equal to BA, B will be constant, it will be area by time, correct? Let's take
Yes,
one length is fixed and another length is changing. So area is like L square, length into breadth. One length is fixed and breadth is changing. So length will come out B into L dB by dt. B is breadth. So change in the displacement by time will be what? Make sense?
Yes, sir.
So you can prove anything, and when you are really good in the derivation, nobody can stop you. If you are good in derivation, nobody can stop you. Okay. What is this written? Second F, second F. It is like if you take second finger in the Fleming rule. In magnetic field, second finger was indicating current. In this chapter, second finger is indicating induced current. So both are different. Direction of current and induced current are opposite to each other. Note it down. Direction of current is opposite to direction of induced current. Make sense?
Yes, sir.
That's why in this chapter, this second finger of Fleming rule is indicating the induced current. But in left hand rule, second finger was indicating current. Sarah, what is the difference between Fleming left hand rule and Fleming right hand rule? Here we have Fleming right hand rule, and in previous chapter we had Fleming left hand rule. Sarah, what is the difference between the Fleming left hand rule and Fleming right hand rule?
Sir, in Fleming's left-hand rule, we have force, and in right-hand rule, like induced current can have.
Okay. If you take Fleming left hand rule, then you had thumb, you had first finger, you had second finger. This is thumb, first finger, second finger. Thumb was indicating force, first finger was indicating magnetic field, and second finger was indicating current. Make sense? These three things. Thumb, force. First finger, magnetic field. Second finger, current. But if you take a right hand rule, this is thumb, this is first finger, this is second finger. Jordan, how is my diagram of thumb, first finger, and second finger? Is it
It
too
looks
good?
like a flower.
Incomplete flower.
Yes, sir, just petals.
Is it really great diagram?
It is better than you were trying to attempt to draw a hand.
Yeah, I think last year I was drawing hand and
Yes,
it
sir,
was very
that we
bad.
remember the diagram.
So it is 1,000 times better than that.
Yes, sir.
Okay. So here you will see the motion of the conductor. It is like force. Here it is magnetic field same. Here you have induced current, not simple current, induced current. And that's why, because when you change hand, direction also become opposite. So we are bothered about this induced current and current. They are opposite to each other. Everything else will be. Understood. Here, force means motion of conductor. Motion of conductor. Motion of conductor. Same meaning. Because wherever you are moving, there you have force. Correct? So better version is motion of conductor. Yes. So when conductor is moving in this direction, magnetic field is inside, then what will be the direction of induced current? That's how we can calculate using motional EMF. Motional EMF formula is BLV using Faraday's second law. Here, if you have a long rod free at one end and it is rotating, then it is rotating. Tell me, who will tell me? Chandana, what is the formula of omega?
So 2 pi by T.
V by R or V by L also equal to 2 pi by T.
Yes, sir.
Correct. So, can we say V will be equal to L into omega? And our EMF was BLV. Instead of V, I wrote L into omega. So, it will be equal to BL square omega.
Yes, sir.
Because you are considering only one end, only one part. So, it will be half amount. Make sense?
Yes, sir.
In this case, if you have two end XA and XB, formula will be same. If you want to calculate induced EMF between A and B, half same formula, B omega same. L is changing from 1 to 2. That's why. Same L square formula, but different values. That's why difference. Make sense, guys?
Yes,
This
sir.
we'll discuss in the next topic in inductance. Lange's law, everything else is done. So this part is done. Go through it once. I am sending the full PDF. Ask me your doubt. Then we'll solve some question, and then we'll move to the last part of the chapter, inductance. Inductance. Then we'll discuss inductance. Send me your notes. No, no, don't send notes because we have to still do. So just 5 minutes. Quickly revise whatever we did. Ask your question, and then we'll continue.